Just for everybody's, understanding information, we are live streaming the entire webinar and we will be recording it as well.
Avana, can we start? Should we give them
Yes,
another?
absolutely. You can begin. Or maybe you want to wait for a minute or so. You already have 22 participants.
Okay, I think let's wait for just one more minute and thereafter we can start. I think we can begin now. All right. Good afternoon to everyone. I'm Abhishek Bhardwaj, and I'm a program associate with the energy program at WRI India. I welcome you all on the wonderful occasion of World Environment Day today. We believe that we don't want to protect the environment, but create a world where the environment doesn't need any protection. For that, we essentially have to nurture the nature so as to have a better future. Before we proceed with the webinar, I would like to cover some housekeeping rules so that the webinar proceeds in a systematic way and you get the most out of it. The event will be live streamed on WRI India's YouTube channel and recorded for record-keeping purposes. Participants joining online must keep themselves on mute when not speaking. Kindly use the question and answer box for queries to the speakers. Our speakers will try to answer some of those questions. The moderator may pick a few questions at the end of the session and pose it to the speakers. Kindly use the chat box for any technical issue, queries, and comments. For feedback, please drop a mail to indiaenergy@wri.org. And finally, all our updates will be on WRI India Twitter handle and the WRI India's LinkedIn page. Let me thank you all for joining today's webinar titled Carbon Capturing for Low Carbon Industrial Transition. This is part 2 of the series of webinars we will be conducting to touch upon the industrial decarbonization aspects. To take you through the agenda, we will be having 3 presentations by the designated speakers and will be followed by a panel discussion and question and answer session. To give you brief on to the introduction of as to why we are planning webinars around the industrial decarbonization aspects. The industrial sector holds a prominent position in the Indian economy, accounting for 31% of the GDP. Industry's relevance can be identified through various direct and indirect linkages with the other sectors, contributing to economic growth and employment. However, the sector is also responsible for a significant share of carbon emissions for India. In the year 2019 alone, overall carbon emissions for India were dominated by the burning of fossil fuels for electricity production and industrial production of materials. With India's pledge to reduce emission intensity of its GDP by 45% by 2030 and long-term goal of reaching net zero by 2070, industries must prioritize decarbonization. India ranks third in the world for CO2 emissions, following China and US, with an estimated annual emission of approximately 2.6 gigaton per year. A sustainable solution is required for the industrial sector, and carbon capture, utilization, and storage can play a crucial role in decarbonizing industries such as steel, cement, oil and gas, petrochemicals, and fertilizers. These sectors are vital to the sustained growth of Indian economy. This webinar is organized as part of Clean Energy Technology Hub. The objective of the hub is to enhance knowledge, gain valuable insights, and accelerate the clean energy transition with panel discussions from industry leaders and government stakeholders on all the latest trends and development in renewable technology, challenges and opportunities, and case studies. The first webinar on industrial decarbonization, Are the Industries Ready for Green Hydrogen, was organized on 6th of April and had many informed discussion on the usage of green hydrogen in the industries. The panel discussion revolved around the development of electrolyzer supply chain in the country, the policy implication that was announced earlier this year, the requirement of an extensive research and development in the area, and besides focused on the roadmap and development for RE infrastructure and grid to support the ambitious green hydrogen targets. We begin today's webinar by presentation by Lalit Sharma on carbon capturing for low carbon industrial transition. Lalit is a senior project associate with the energy program at WRI India. He's working as an energy efficiency professional with the knowledge of working across various dimensions of energy efficiency improvements in the industrial sector and supporting transformational projects. Lalit is an electrical engineer with BTech certification from Punjab Technical University, Jalandhar. He holds a 3-year diploma in electrical engineering from PBSTE and IT Chandigarh. Over to you, Lalit.
Yeah, thank you, Abhishek. So I think my presentation is visible.
Yeah, we can see your screen. Please.
Yeah. So thank you, Abhishek. Hello, everyone, and good evening. So CCUS is a innovative technology that aims to the capture carbon dioxide emission for various sources, store them safely, and harness their potential for economic and environmental benefits. So in this presentation, we'll talk about the significance of the CCUS, its potential, and its role in India's journey towards the low carbon economy. So first is why industry. So as we all know, India has set their target to become net zero by 2070. To achieve this target, industries must act on it. So as per Global Carbon Project report in 2021, India contribute almost 7.5% of the global emission. If we look India's emission, then the energy sector contribute approximately 53% and the industrial sector contribute 25% of the emission. So more focusing on the industrial emission, 60% contribution is from steel, cement, chemical, and the fertilizer sector, and these are the hard to abate sector. So what are the decarbonization options for the industry sectors? So decarbonizing the industry is a crucial step in mitigating the climate change and reducing the greenhouse gas emission. There are several options available to achieve this goal. So first is about the renewable energy transition. Shifting from fossil fuel-based sources to renewable energy is a key component of the decarbonization. This involves increasing the use of solar, wind, hydro, and geothermal energy to power industrial operations. So second one is the energy efficiency. Implementing energy efficiency technology and practice can significantly reduce energy consumption and carbon emission in the industries. Electrification, transitioning from fossil fuel powered machinery and vehicles to the electric alternative can help decarbonize the industry. CCUS technology that we are talking about today. So CCUS technology is like capturing the carbon dioxide from the industrial process, transport it to the storage site, and either store it permanently underground or use it for the other purpose, such as enhanced oil recovery and the manufacturing process. And then the sustainable biofuels, replacing fossil fuel with sustainable biofuels can significantly reduce carbon emission in the transportation and aviation sector. So these biofuels can be produced from feedstock like agriculture waste and the dedicated energy crops. So green hydrogen, producing hydrogen using renewable energy through electrolysis creates green hydrogen that can be used to clean energy source in various industrial process, including steel production, chemical manufacturing, and the transportation. So already discussed green hydrogen in our last previous webinar. So we'll also share some key learning and highlights of that webinar in my last slide. So it's also important to note that industry may require specific decarbonization approaches to their unique characteristics and the challenges. So what is the CCUS? So capturing CO2 emission from industrial process, power plant, and other high emission sources is called carbon capturing. And how we can capture it? So there are some technologies, methods like pre-combustion, post-combustion, and oxy-fuel combustion methods. So in pre-combustion method, this method involves converting fossil fuel into the mixture of hydrogen and carbon dioxide through process like gasification. The CO2 is then separated from the hydrogen using various techniques as the pressure swing, absorption, and the membranes. In the post-combustion method, CO2 capture from flue gases emitted by the power plant or the industrial facility after the fuel has been combusted. So technically, like solvent scrubbing, membrane suppression, or solid absorption are used to capture CO2. Then the oxy-fuel combustion. In this process, fossil fuel are burned in the atmosphere of the pure oxygen instead of air, resulting in the flue gases primarily composed of CO2 and water vapor. The CO2 is then separated from the water vapor for capture. So CCUS facilities currently capture almost 45 million ton of CO2 globally, but that needs to be increased. Once the CO2 is captured, then the next step is utilization, converting captured CO2 into the valuable products such as chemicals, fuels, and the building materials. So one is the enhanced oil recovery method, can be injected into oil reserve to enhance oil recovery. This method allows us for the permanent storage of CO2 while increasing oil production. Then the chemical and fuels, CO2 can be converted into chemicals such as methanol or urea, or transformed into the synthetic fuels like methane or dimethane with the chemical reactions. Mineralization, CO2 can be mineralized by reacting in the with certain type of minerals such as basalt to form the stable carbonates, which can be stored or used for the construction material. Around 230 million ton of CO2 are currently used each year in mainly fertilizer industry to manufacturing the urea. Once the CO2 is captured, then this CO2 needs to be transported and stored into the prevent it from being released into the atmosphere. Carbon storage typically have we can say two methods like geological storage. CO2 is injected deep underground into the suitable geological formation such as depleted oil and the gas fields or the deep saline aquifers. So these formations should have a secure top rock to prevent this CO2 leakage. Then the ocean storage, CO2 can be injected into the deep ocean waters with, where it can be dissolved and sorted. However, this method requires careful monitoring to mitigate potential ecological impact. So the British Geological Society and IIT Bombay indicate a large potential of CO2 storage in India, around 400 to 600 gigaton. So it's important to note that the specific technology can process involved in CCUS can vary depending on the source of CO2 emission, the industry involved, and the geographical location as well. Then coming to the CCUS towards sustainable future. So CCUS can help us in climate change mitigation, meeting the emission reduction, industrial sector decarbonization, sustainable energy transition, enhancing energy security, economic opportunity. So overall, CCUS is necessary for the Indian industry to reduce greenhouse gas emission, meet climate targets, decarbonization intensive sector, foster a sustainable energy transition, enhance energy security, and create economic opportunity as well. So it can contribute a cleaner or more sustainable future for the Indian industrial sector and the country. So after this, some of the key challenges as well they have. So cost, implementing the CCUS technology is generally expensive. The high upfront cost involved in setting up a CCUS facility, transporting and storing captured carbon, and retrofitting existing industrial plants make it economical challenging, so especially for the developing countries like India. And these then scale and infrastructure to deploy CCUS at a significant level. India would require extensively infrastructure for capturing, transporting, and storing carbon dioxide. So building the necessary pipeline storage facility and the associate infrastructure across the vast and diverse India landscape is significant and logical challenge for it. Technology readiness is a challenge. While CCUS technology have been deployed and demonstrated at a small scale level. So there is need to scale up this technology for large scale deployment. Then the energy consumption is a major challenge. To capture carbon process require additional energy, which can increase overall energy consumption of the power plant and the industrial facility. This can impact the overall energy efficiency and increase the operating cost of that plant. And coming to the regulatory framework, establish a comprehensive regulatory framework for CCUS is crucial to address legal policy and liability issues. Developing appropriate regulation for carbon capture, transportation, and storage as well. Ensuring the long-term liability and safety of storage site requires careful consideration. Public acceptance and awareness of CCUS technology are important for their successful implementation. Educating the people about the benefit, risk, and the potential environment impact of CCUS is a crucial governance support and address any concern related to these technology. Then the financing and the investments, securing, educating, funding and investment for CCUS project is a significant challenge. Given the high cost and the risk involved, attracting public and private investment for large-scale deployment of CCUS technology in India requires innovative financing mechanism and supportive policies as well. So now India's CCUS scenario. So IIT Bombay established the first ever National Center for the Carbon Capture and Utilization. Tata Steel commissioned first India plant CO2 capture from blast furnace gas at Jamshedpur. The Tuticorin plant stands the first industrial scale-up example for the successful CCUS, and Mr. Ram with us, we know more about it. And the ONGC has signed a MOU with global petroleum giant, that is Shell, for the cooperation with the CCUS studies. So these are some India's scenario. Learning from the last webinar, and as Abhishek said, we have organized a green hydrogen webinar on 6th of April. So the key learning from that is like first, I think the cost, the high production cost of green hydrogen remains the main barrier for the adoption, with around 70% of the cost contribute to the production. So that is the one. Second one is the steel sector. In the steel sector, we can blend the green hydrogen with other fuels to minimize the carbon footprint. Whether the availability of scrap in India might not be sufficient to meet the increasing demand for the future demand for the steel in the future. And the third one about the electrolyzer technology. So India, we found that India falls behind other countries. So resolving this challenge, so there should be some efforts from the international and domestic collaboration should be required at both the national and subnational level. Few pathways and the development action has been taken by the government of India. So these are from learning from the last webinar as well. So with this, I am ending with my presentation. Thank you, Abhishek. Over to you.
Thank you, Lalit, for that presentation on the carbon capture utilization technology, and elaborating on where India stands currently and what are the challenges related to it. Next we have with us is Mr. Mehboob Abul Naga, who's a solutions fellow at the Center for Climate and Energy Solution in Washington, D.C. His work includes research and analysis of clean energy technologies, as well as energy and environment policies. His work also engages business representatives on energy transition, carbon management technologies, and industrial decarbonization strategies. He writes and communicates information on the overreaching topic of climate and clean energy technologies. Mr. Abul Naga was part of the inaugural class of Obama Scholars at Harris School of Public Policy, University of Chicago, where he earned an MA in International Development and Policy with a focus on energy and environment policy. He holds a MS in Sustainable Energy Engineering from CET-H Royal Institute of Technology in Stockholm, and MS in Environment Management from Universidad Politécnica de Madrid, and a BS with honors degree in Petroleum Engineering from Suez University. Over to you, Mr. Mahmood, for a presentation on carbon capture, a pathway for industrial decarbonization.
Thank you so much, Abhishek, and thank you for WRI India for having me. I will just start by sharing my screen. That's possible. if you can just confirm that you see my screen, it would be great.
Yes, Mahmood, we can see your screen.
Perfect. Again, thank you. Good morning, good afternoon, everyone, depending where you are. My name is Mahmoud Abunaga. I'm a Solutions Fellow at the Center for Climate Energy Solutions. And in case you're not familiar with CET-H, we are a nonprofit, nonpartisan think tank based in Washington, D.C. We work with policymakers, local communities, academia to promote climate and energy solutions by bringing these stakeholders together along with businesses to reduce emissions, expand clean energy, and strengthen resilience to climate impacts. So today, I will be mainly talking about the role of carbon capture technologies and carbon management in general in industrial decarbonization. I prefer to use the term carbon management to refer to the different technologies for carbon capture, whether from point source like industrial facilities or power plants, or even from directly from the air, or as some people refer to as carbon dioxide removal, or CDR. I'm sure you all heard about the Intergovernmental Panel on Climate Change, or the IPCC report. And in this report, they model basically the evolution and breakdown of emissions from now till the end of the century. And they highlighted 4 main scenarios that you can see here on the right. If you look at these different highlighted scenarios, you will notice that they have common features. First, full decarbonization of the power sector and deep emission reductions in the transportation and the industrial sector, and some degree of contribution from carbon management technologies. So the degree of the contribution for carbon management would vary depending on how much we reduce emission. Simply, the more we manage to reduce emissions, the less we will need carbon management solution, and vice versa. But these solutions need to be part of our decarbonization strategy nonetheless. And why do we care about that? Especially, I will be talking about examples from the United States, but I think people in developing economies should be paying close attention to this technology. And I come from a developing nation. I'm originally from Egypt. Because every development scenario for developing countries have some degree of higher level of industrialization in the future. So the question becomes not how to slow down this industrialization activity because they are directly connected to economic development target. The question becomes how to decarbonize these activities and make sure they can be part of a low carbon economy. And you can see here that these industries, if they were not retrofitted in the future, we could risk emitting more than 600 billion tons of CO2 over the next 50 years with the level of industrialization that we expect. As Lalit mentioned, like basically this is how the different technologies for carbon capture works. There are different approaches, but simply they work under the same concept. Flue gas is basically fed into an absorber where the solvent, or whether it's chemical or physical, will react with carbon dioxide. Then the CO2 rich solvent now will be transferred to a regenerator, where basically the temperature will be raised to allow for the separation of this absorber and the CO2. And now you have pure CO2 that you can compress and transport, and a fresh solvent that you can feed back into the system and reuse again. So depending on what industrial sector we are, or what industrial application we're discussing, they can choose what will best be compatible with their system. So if we're talking about like steel plant, maybe the oxy-combustion system will work well for them. Other plants that they don't necessarily need any disruption to their operation, the post-combustion system will be suitable for that. But also it's a function of the concentration of CO2 in the flue gas stream of these industries. Let's take a closer look at the different applications and the cost associated with them. So globally, we have around 30 operation facility for carbon capture, utilization, and storage. And I think around 10 or 11 in currently under construction, and over 150 in development. So we expect by 2030, hopefully, that we'll have something close to a 200 facility operational by then. In the United States, and this data is from the United States, Currently, we have 13 different operational facilities with a capacity to capture a little bit over 200 million, sorry, a little bit over 20 million tons per year. And there are also more than 70 facilities under construction. If you look at the left part of the graph, most of the facilities to date in the United States and globally have been in two main applications: ethanol fermentation facilities and natural gas processing facility. And why is that? Because of the high concentration of CO2 in the flue gas stream of these two particular applications. It basically only requires some degree of dehydration before the carbon dioxide can be compressed for transport and storage. In general, the more concentrated CO2 in the flue gas stream, the less expensive and the less energy intensive it is to separate it and capture it and then go along the value chain of transport and storage. And that's why the cost of CO2 is mainly a function of the concentration of CO2 in these flue gas streams. For now, the main vehicle for revenue for carbon capture in the United States is what we call 45Q tax credit. 45Q, it refers to the certain or the relevant tax section in the tax code. And it basically provides companies with up to $85 per ton for capturing carbon from point sources and injecting it in saline aquifers permanently. If the companies that wish to use the CO2 that they have captured for other applications like fuels or any other like materials, low carbon materials, then the credit level will become $60 per ton. So that has happened recently, and we will discuss the policy later, but that's the main revenue now. For sure, if you produce certain products, then you get revenue from these products as well. This data here is from India, and I think our next speaker also are from Dastor, and they can share more details about their great report there. But if you look closely, you will see the same pattern when it comes to cost. It's a function of the concentration of CO2 in the flue gas stream. So the heavy industries, whether it's cement or iron and steel, you can find him like in the middle of the range, or at least a little bit towards the right. And there will be need for some supportive vehicle, whether it's tax credit or other forms, to make these industries break even, because at the end, these industries they trade in global commodity on relatively narrow profit margins. So if the CCUS will add cost to them, they need to make sure that they can still break even and be competitive in a global market. Why do we care so much about CCUS in industrial facilities or industrial applications in particular? Because many of these applications or many of these industries, even if they are completely powered by clean energy, and let's assume for a minute that the clean energy that you have in the grid can reach the power, the heat and electricity needs of all your industrial facilities. Even if they are powered, they still will emit carbon because, for example, the cement industry, 60% of the emission from the cement industry is process related, not combustion related. So even if you power them with clean energy, they will still emit carbon. So that's why there is a need for carbon capture at these facilities to completely decarbonize. You can see here data from about the share of non-combustion emissions from different industries to the share of the total emissions or the total non-combustion emissions from these sectors. Data for India is incomplete, but I hope some of the speakers today can also share that with us. That would be great. I couldn't find them in the UNFCCC database, and that will be really good to focus or zoom in a little bit about the exact emissions that we are talking about. Hard to abate non-combustion emissions, I mean. The other piece of the CCUS is the utilization piece. And now there is a lot of focus on like carbon recycling and make sure that we are part of a circular economy. So basically carbon recycling technologies, carbon utilization, they use carbon dioxide as a feedstock for synthesizing chemicals and fuels. one of the most mature conversion pathway is direct conversion of CO2, or what people call hydrogenation, to different value-added hydrocarbons. These can be methanol, ethanol, olefins, or other things that you can use also as intermediate for other end products. But this process requires a catalytic reaction that needs high energy input. And by this can be added in the form of electricity or high energy reactant like hydrogen. And I know, like last session or last webinar, we talked about hydrogen. Why do we need that? Because we need to overcome the strength of the carbon-oxygen double bond in the CO2. It requires that catalytic reaction. So the climate benefits of this hydrogenation process will be dependent basically on the source of the hydrogen. The less intensive it is, the higher the environmental impact of it. Another utilization pathway is the mineralization, which basically involves the reaction of carbon dioxide with alkaline sources to produce solid carbonates. And this is a promising opportunity for hard to abate sectors as well, because now we can talk about like low carbon concrete or low carbon cement, and that will be a great opportunity to help that sector on both sides, not just to capture the carbon, but also to increase the competitiveness by creating low carbon products in that sector. Are also other forms of biological uptake, but I think these still need more time to develop and research, at least to be competitive at scale. One thing I will talk about when we talk about storage, there are different techniques for storage, and basically we try to imitate nature when we talk about storage. If structured trapping, for example, that's basically how natural oil and gas occur, and they will be held in place by basically layers of low permeability rock on top, or what we call a cap rock, and they prevent any upward leakage, and they will be stored in porous rock to the sides, basically containing the fluid that's denser than that. There are different techniques, like whether it's residual trapping, solubility trapping, or mineral trapping, and this just to give you an idea that saline storage or durable carbon storage has been demonstrated for years. Like we have this process dates back to the 70s in some applications for EOR, but also for dedicated carbon storage since 1996 we experience with that as well. And now let's talk a little bit about the supportive policy framework, and we'll share some examples here from the US from the recent bipartisan infrastructure law and the Inflation Reduction Act. There have been, these policies are considered like the greatest contribution to the support of carbon management technologies to date, with like cumulatively, we're talking about $12 billion investment in carbon management technologies, whether for preparing infrastructure for geologic storage or pipeline infrastructure, and also the permitting for these facilities. I want to focus a little bit on the 45Q here, because as I mentioned, it's the main vehicle for supporting these projects. And you can see here the different enhancement that happened with the Inflation Reduction Act when it came to 45Q. So for sure, the $15 per ton before was good for certain applications, but not for most industrial application. And that's why when we see the $85 per ton now, we have seen an increase or an influx of different applications for CCUS deployment in heavy industries, because the $85 per ton would make them close to their break-even value and makes it more attractive for them as an investment. And I think other countries should be looking to similar vehicles that can support these industries. And just to clarify the point here about the $180 per ton, for sure, like point source capture is more mature than direct air capture from the air, and also less challenging. So that's why the credit was enhanced to create another level that separates direct air capture from point source capture, and dedicating larger or a much more generous credit for direct air capture by $180 per ton for saline storage, and $130 per ton for carbon utilization. This credit level is over 12 years, as long as the project commences construction before the end of 2032. Another important concept when we talk about the commercialization of these facilities and the expected increase of number of facilities is a new model that's called the hubs and cluster model, which basically separates capture from transport and storage infrastructure and investment. And you can see the value of that because basically by creating this shared infrastructure, it allows risk sharing among the different public and private organizations participating in these projects. Building regional CCUS network would also create opportunities for project developers to increase the scale of CCUS projects. So instead of like few megatons, we can talk about even larger than that. And it would also help accelerate the adoption and commercialization of other carbon dioxide removal technologies. So the more nascent technologies can benefit from this shared infrastructure as well. And I think when we talk about the scale that we need, we are orders of magnitude away from what we need by 2050 or by 2070 in case of India for their net zero target. And that's why economies of scale using this hubs and cluster model will be really critical to make that happen. And I'll just highlight a few examples of global partnerships on CCUS. In earlier this year, during the Major Economies Forum, the Carbon Management Challenge was announced, and with the goal of basically accelerating carbon management from point sources and also from the air. And we expect the goals, more concrete goals will be announced by COP28. And so far we have like 10 countries that are participating in the Carbon Management Challenge. Also, the Clean Energy Ministerial CCUS initiative has been a great initiative with more than 14 different countries participating in efforts to enhance the R&D activities around CCUS technologies. US and India have a strategic partnership in that regard. Japan as well have.
I'm so sorry, I have to stop you here. Actually, in the interest of time, I think we'll have to, move to the conclusion part of your presentation. We have one other speaker lined up, and we are waiting for the panel discussion to start. So, would really apologize for this, but we'll have to move forward.
No, that's totally fine. That's my last slide.
Sure. Please.
So it's just examples. We can chat a little bit about this in the panel discussion, but this is examples of the different countries that are cooperating on CCUS technology. And with that, thank you, and over to you, Abate.
Thank you, Mahmood, for this presentation. I think the role of carbon management, the process and the technologies and the cost and revenues that shared were quite interesting to know. Next we have with us is Mr. Gaurav Verma. He has shared his screen. He's the DGM at Business Development and Branch Head at MN Dastoor & Co. Adept at working out optimized solution for conventional and emerging technologies. Gaurav assists interested stakeholders in developing feasibility for adoption of carbon capture solutions. He looks after CO2 emission abatement initiatives and integration of CCUS-based clean energy solutions in steel, power, chemicals and energy industry. Gaurav is BTech Mechanical from AMU and has management degree from Indian Institute of Foreign Trade and CCS, a certification from University of Edinburgh. Over to you, Mr. Gaurav.
Thank you so much, Abhishek. So that was a wonderful presentation from Mahmood and Lalit, and actually they have made my life slightly easier. To start with, I would like to say that India as a country, we are the growing economy and we have been blessed with huge coal endowments, and we cannot compromise on our economic growth. And at the same time, we have to also take care of rising GHG emissions. So in this regard, CCUS is definitely going to play a vital role in ensuring low carbon and sustainable future for India. Either we prevent CO2 from entering the atmosphere, or maybe we'll have to remove the excess CO2 which is already in the atmosphere. As is clear from this picture that investments in the CCUS are increasing around the world. But countries with operational CCUS are the ones which have enabling policies for the same. Likewise, 45Q tax credit in US, which my friend Mahmood has already explained. Similar to this, Canada also have tax credits. Denmark is investing 2.2 billion towards CCUS development. And in the end, South Korea has also announced plans to invest 1.2 billion towards CCUS development. And as we can see from this picture, in the year 2022, most 97 million tons of CO2 capture capacity is at advanced development, 91 is at early development phase. So coming future, yes, we will see a lot of CO2 operational projects around the world. We need to appreciate and understand that CCUS is not just a single point cost, but it is a consolidation of costs incurred across various points in the entire CCUS value chain. Starting from technology selection, each industry has different cost structures, and majorly CO2 capture cost depends upon the CO2 concentration in the stream. Transporting CO2 to the intended location will also add some cost. So again, we'll have to optimize this. And finally, CO2 sequestration and utilization. CO2 sequestration is one of the most economical means to dispose of the CO2. But however, utilization, making methanol, building aggregates, fuels, and nanomaterials will provide for the economic benefits out of this CCUS. As CCUS is not yet established in India, so it has its fair issues and challenges. So let's see how we can address. Number one, the most important, green premium. Who is going to pay for the expensive low carbon products? So in this regard, some preferential procurement or carbon subsidies from the government will be definitely welcomed. Number two, technology selection. So there are a number of carbon capture technologies which are proven and are already operating at commercial scale. But however, we need to appreciate that each industry has different cost structures, and the same for the carbon capture technology, which is as low as $15 per ton in case of gasification on the hydrogen generation, and it goes up to $40 to $50 in case of power sector. So selection of appropriate technology is the first step towards a viable CCUS scheme, and this will also ensure ease of retrofitting in the existing facilities. So in this regards, sponsoring feasibility studies for the large-scale CCUS ecosystem will be very much helpful. These are most of the technologies which are available at this point. Pre-combustion, post-combustion, which is physical solvent-based and chemical solvent-based, and the approximate cost from of CO2 capture is also being mentioned here. However, direct air capture and calcium looping are something which are new but need some development. So in this slide, I have listed out 3 of the most popular solvents. The gas components which are listed below the carbon dioxide and which have the solubilities more than 1. So these are the components which will actually poison the solvents, which will reduce the solvent regeneration rate and will increase the parasitic load on the facility. So it is very important to map the solvent as per the flue gas components. So if there is some problem, then the OPEX will go up, which will affect the viability of the project. Number 3, scalability. India has potential of around 600 gigatons of CO2 storage capacity, but however, infrastructure needs to be developed in form of hub and clusters model, and also a pilot project should be commissioned for CO2 storage. So to an extent, my friend Mahmood has already spoken about hubs and cluster model. So this is just a pictorial representation how a hubs and cluster model will look like. So we will further deliberate on hub and cluster model in a case study, which I have prepared for this. And finally, the CO2 movement. So in US, I think almost 9,000, in North America, sorry, almost 9,000 kilometers of CO2 pipelines are operating. But however, in case of some unfortunate mishap, there is a possibility of spillover to the upcoming project. So from India's point of view, we need to have very clear guidelines on CO2 liability, ownership, insurance, and transportation. But saying all that, CCUS is not a new concept. It has been already operating for the last 40 to 50 years. Likewise, a few successfully operating CCUS projects around the world. In Abu Dhabi, Amirat Steel Industries has already captured almost 4 million tons of CO2 since 2016. Boundary Dam project, which is a poster boy of CCUS in power plants, has captured over 4 million tons of CO2 till date. And finally, the Great Plains Synfuels North Dakota plant, more than 38 million tons of CO2 has been captured since 2000. So technology is there. We have to map it to make it viable. This is one of the engineering feasibility which Dastur is carrying out right now. It is a US DOE funded project for industrial scale CCUS project integration in the existing steel plants. It is for Cleveland Cliffs steel plant wherein 2.8 million tons of CO2 will be captured for geological sequestration. And this is a 5 million ton integrated steel plant. So what we are doing here, from the blast furnace gases, CO2 will be removed and CO2 will be sent for geological sequestration. And however, the remaining syngas will be fed through a gas conditioning unit, and by utilizing water gas shift reactor, the percentage of hydrogen will be increased in the syngas. And this now rich syngas will be sent to existing power plant for increasing the electricity generation. And moreover, considering the utility of hydrogen towards green steel making in the future, a provision of hydrogen facility is also being kept in this conceptualization study. So in the last slide, we talked about one industry. So now we'll talk about how a self-sustainable CCUS viable model can be created. So this is a proposed conceptualization for Humber Industrial Cluster Plan, which is aiming to be world's first net zero by 2040. Just to introduce, this Humber Industrial Cluster accounts for almost 5% of UK's entire carbon emissions. So in this hubs and cluster model, this gas-fired power plant will be the anchoring plant, which will ensure a steady supply of CO2 to the CO2 pipeline. And all the industries coming in this region will contribute towards CO2 from the respective carbon capture plants. So pipeline infrastructure will be shared here, and there will be a centralized CO2 compression facility. And finally, the CO2 will be stored under southern North Sea. And this project aims to capture around 10 million tons of CO2 by 2030. But okay, this was CCUS for the existing facilities. Now coming on to the hydrogen, this project has a provision of producing 170,000 tons of blue hydrogen per year. Mind you, this is a blue hydrogen because economics has to be taken care of. In the battle between technology and economics, technology has never won. So this is a blue hydrogen production from natural gas. Again, this will be integrated with CO2 capture facility. And this blue hydrogen will in turn decarbonize heavy industries, transportation, heating, and power industries. So with this, I can reasonably conclude that the problem is CO2. Problem is not the fossils. Problem is not coal, gas, oil, or anything. Renewables, yes, they are the potential, but they can address only a certain part of the emissions. And economic viability is the fundamental to make our skies clean. And in this regards, Since India, we are a growing economy, we cannot compromise on our growth rate. So CCUS is going to be an integral part of decarbonization scheme. So now just to introduce about our company, MM Dastur Energy, we are one of the India's oldest engineering consultants. And right now we are carrying out decarbonization studies for the steel this is Steel Authority of India Limited, Bokaro and Rourkela steel plants. Cliffs, we already have discussed. We have finished the CCUS deployment policy mechanism report for Niti Aayog, which is under consultation with the government. And we are also carrying out one CO2 to methanol conversion feasibility study for an integrated steel plant in India. And these feasibility study for IOCL, wherein the captured CO2 from Koyali refinery will be used for enhanced oil recovery in ONGC Gandhar oil field, has been finished. And other than this, we have also carried out feasibility studies for ADNOC and BPCL, wherein they wanted to have a gasification based ecosystem integrated with carbon capture products. So thank you so much for this opportunity, WRI team. And so I pass the baton back to Abhishek.
Thank you, Gaurav sir. Thank you for elaborating on the challenges, the case study specifically, and telling about the transportation and movement around the carbon capture technologies. So now we have the panel discussion with us. Sir, I would just like to give a brief introduction as to. Just let me share my screen. Yeah, just to briefly introduce the panelist members one by one. We have Dr. Ankita. I'm so sorry. Yeah. We have Dr. Ankita Gangotra, who's an associate at the climate program at World Resource Institute. Ankita Gangotra is prior to joining WRI, Ankita was a postdoctoral research fellow in the School of Foreign Service and Department of Physics at Georgetown University. Her research looked at readily available technology and policy options for upgrading low carbon cement production in the United States. Her research looked at readily available technology and policy options for upgrading low carbon cement production in the United States. Ankita has an integrated master's in electronics engineering and nanotechnology from the University of York, UK, and a PhD in physics from the University of Auckland, New Zealand. She has also previously worked as a measurement scientist on projects related to regenerative agriculture, native reforestation, and biodiversity. We welcome you, Dr. Ankita. Next, we have Ms. Devika Vattal. Ms. Devika Vattal is a leading expert in CCS and CCUS in India and currently serves as an innovation consultant for the Global Cement and Concrete Association. She holds a master's degree in chemical engineering from Indian Institute of Technology, Delhi. With 15 years of experience, Ms. Vattal has worked with organizations such as ADB, Reliance Industries Limited, Beltel Science and Technology Limited, and ISRO. Her expertise includes techno-economic assessments and feasibility studies, process engineering, and technology and market trend landscapes for carbon capture and utilization. Ms. Vattal also serves as an advisor to the Climate Policy Initiative India to help in development of policies and financial framework for India, and has also mentored and consulted technology-based startups on proof of concept experiments, process optimization, prototyping, and scale-up, as well as business strategy and operation. Welcome, Ms. Devika. Next, we have with us is Mr. Ramachandran, who's a chemical engineer and obtained his BTech degree with distinction from NIT Tiruchirappalli, Tamil Nadu in the year 1973. Later, he acquired an MBA degree from the Madras University. He has been with SPIC Group for the past 48 years. Prior to this, he was the managing director of Manali Petrochemicals Limited. He has wide experience in designing and erection of commissioning of petrochemical and fertilizer plants. Mr. Ramachandran worked in the commissioning team of fertilizer plants for NFL and ICI. He has design experience of plant by association with projects in SPIC, TFL, and MPL. He was instrumental in the implementation of a project to separate CO2 from boiler flue gas, which is the feedstock of manufacture of soda ash. We welcome you, Mr. Ramachandran. Our third and fourth panelists is Mr. Mahmood and Mr. Gaurav, who you earlier heard speaking. Finally, the session would be moderated by Mr. Sripati. Mr. Sripati is a project associate at WRI India. Sripati's primary area of work revolves around new energy technologies, focusing on up-and-coming green technologies to achieve a smoother clean energy transition across India. Prior to joining WRI India, Anirudh completed his MTech in Energy Studies from Indian Institute of Technology, Delhi. There, he worked on solid-state hydrogen storage systems and solar radiation prediction modeling. Over to you, Anirudh.
Thanks, Abhishek. And hello, everyone. And I would like to thank the esteemed panel members for their time to participate in this webinar session. Hope I'm audible, Abhishek.
Yes, Sripati, we can hear you.
Okay, thanks. So for the next 30 minutes, we have a little bit of a time crunch here. So for the next 30 minutes, we'll be discussing about the carbon capture and related potential for low carbon industrial transition in India. So without wasting further time, let me focus my first question towards Mr. Gaurav Verma. So yes, sir. So I first want to break the ice on this thing: long-term carbon storage versus carbon capture and utilization. Which suits India the more? Are there enough availability of this geological formation and natural crevices to go for long-term storage option in India based on your studies, sir?
As per the initial studies have confirmed, we have almost 600 gigatons of permanent storage capacity available. However, the dedicated geological studies on pore space mapping and geological formation has to be carried out, because we have been blessed with a very long coastlines. So the availability of saline aquifers is also there. But however, we need to carry out geological studies to locate these basins. Okay,
understood, sir. And also, you explained about the study on the hub and cluster model that you are currently undertaking with the Niti Aayog. So, like, what is the possibility for having a cluster model for carbon capture utilization model, sir, in India?
Okay, in India, we have a lot of industrial clusters, and some of these clusters are also located nearby to the coastal areas. So in this hubs and cluster model, one major emitter, like any steel plant or any power plant, they can act as an anchoring facility for the CO2 emissions. And all other small or ancillary industries, they can carry out CO2 capture in a modular form or by their individual carbon capture facilities, and they all can contribute towards a common CO2 capturing pipeline. So this will ensure we have the availability of CO2. The more is the availability of CO2, better will be the economics of any utilization process. And finally, we as a country, we are importing a lot of chemicals, likewise methanol. And then we can also have this CO2 towards production of methanol as an integrated facility catering to all these clusters.
Okay, understood. Yes, sir. One last question for the current round of discussion. So which industry will be the major benefactor if the CCUS comes into mainstream commercialization aspect in India?
We have to carbon capture is a reality. If not today, tomorrow, or maybe day after tomorrow. So there is no escape to this. We'll have to take care of our emissions, despite the fact that we keep on saying that in India, per capita CO2 intensity is only 2 tons as compared to US, which is 15 tons. But we also need to see the area of India and US. That will paint a different picture.
Understood. But like, which will be the early adapter? Which industry segment will act as? Yeah.
So since we are on a economic growth trajectory, and our national steel mission is saying 300 million tons of steel production by 2030. So we'll have to make almost 150 million tons of steel capacity addition. So 100 million tons of steel capacity is almost 400 to 450 million tons of CO2 emission. So I have this ready sector at my hands where I need to integrate carbon capture facilities.
Okay.
And
Understood, sir.
mind you, if I don't, our exports will be prohibited. Either I pay the taxes like CBAM and the green tax, CO2 tax likewise, or we invest here to make my steel, which we can call as green.
Understood, sir. Thanks. Thanks, Mr. Gaurav. Let me direct my focus to Mr. Mahmood. Also, Mahmood, sorry that the final presentation about the collaboration aspects got very limited time during your presentation session. So I just wanted you to elaborate on those aspects now in the discussion.
No, thank you for the opportunity. It was just mainly to give examples that, as Mr. Gaurav just mentioned, the attention to CCUS and carbon management now is like nothing we have seen before. So the cooperation is not only limited to the US, Canada, and countries in Western Europe. It's all the countries are involved now, because if you are a major producer of certain like commodities, like whether it's steel or concrete, which is like the most traded element on earth today, you will need to make sure that you're competitive in future market, and CCUS can give you an opportunity to do that. The only aspect of that is like currently the technology is expensive, but it wouldn't stay expensive all the time. So which countries will adopt it first? Which countries will bring the cost down? Sometimes we tend to underestimate the value of learning by doing and how learning by doing can bring the cost of these technologies down. I personally see a responsibility for major economies to scale the technology, bring the cost down, and then transfer it to developing economies, because these developing economies are not responsible for the climate crisis for the major part. So they shouldn't basically slow down their attempt to achieve a better quality of life and higher level of industrialization, and it shouldn't be a compromise or a trade-off between economic development or sustainability. We see these two things going hand in hand, and the way to do that for developed economies, to scale the technologies, work on them, bring the cost down, and then allow transfer of patents. Transfer of patents for low carbon technology in general is very limited from the global north to the global south today. That's also an important element.
Understood. So in this case, also, as Mr. Gaurav mentioned, this is inevitable. If you are having a decarbonization roadmap and you have a net zero target for 2050 or 2040, then you have to get into this space. So at one point or other, it's going to be a mandatory thing to do. So in that case, if industry is supposed to adopt CCUS, what kind of techno-economic shock that they must be aware of?
As we mentioned, many of these technologies or these applications work on like very narrow profit margins. So in order to maintain your competitiveness, you need to make sure that you break even. So without the existence of like a supportive tax credit or some revenue stream, because today there is no global price on carbon, which basically means everyone is subsidized. So unless we have a price on carbon and companies can monetize the value of the carbon they capture, there will be a gap there. Most of the work, the policy support happening on the CCUS front to date has been the carrot side, the tax credits, like less on the stick side. But we have started to see that in the US, like a few weeks ago, there was a proposed rule by the Environmental Protection Agency for power plants. So now we see coal and natural gas-based power plants thinking about the ways they can reduce the intensity of their megawatts, basically, of electricity by using whether carbon capture or hydrogen, or mix of both, co-firing, different techniques. But now the sticks will also need to play so that we move the industries little by little. It should be for sure a hybrid between carrots and sticks. But to date, mostly sticks, where we have seen that, and maybe they were needed because still like a nascent market.
Understood. Thanks, Mohammed. Now let me request Dr.
Mr. Anirudh,
yes.
with your permission, may I add something to what Mr. Mahmood has?
Sure. Please do.
let's say if we go back in time, in the 1960s and 70s, there was a problem of acid rains, which was affecting the areas hundreds of miles away. So then we saw the concept called desulfurization, and very soon all the desulfurization units were integrated to the power plants. Again, it was an expense at that time, but very quickly in the next 15-20 years, nobody asks about why this desulfurization units. So yes, technology, maybe it is expensive at this moment, but very soon, 15 years or 20 years down the line, it will be very reasonable and economical. It's all supply and demand.
Understood. Yes, Karo. Thanks for the indicator. So now let me direct the question to Dr. Angita Gangotra. Hello, ma'am. So we have been talking about US case studies a lot. Dr. Mohammed, as well as the presentation, it focuses a lot on US's policy structure for CCUS. So, ma'am, could you give us a brief on how the CCUS adoption started in US? What was the primary reason for US adopting CCUS measure? And also, if you can suggest that which industry segment has the most potential, which is using CCUS for mitigating their emissions in US? If you can provide some light on that, it would be great.
Yeah, sure. Thanks, Shripati, and thank you for the invitation to this panel, and thank you to the presenters for your lovely and informative presentations. I can talk about this from a US perspective, but let me first get into the barriers that exist, right, and what the US is trying to do in terms of CCUS. And this is all from an industrial decarbonization perspective. So the hard to abate sectors, and I'm going to give examples from cement mostly, but yeah, this includes cement and steel, etc. So the barriers really, as I see it, are threefold. There's the cost of the equipment for new installations and retrofits for CCS, basically. The cost of the transportation, right, and storage infrastructure in the pipelines. And something that perhaps we haven't discussed so far, which is the permitting or the regulatory processes that are needed for example, for geological sequestration, etc. So the US has been getting serious about CCUS for a while now, but within the industrial sector, if we look at the policies that have come up, and this isn't just to do with the industrial sectors, but I'll name two main policies that have really kicked up the momentum for CCUS in the US, and they are the bipartisan infrastructure law that went into force in 2021, and the IRA, which is the Inflation Reduction Act that went into force in 2022, right? And if we look at the industrial sector, there's about $20 billion that mentions the industrial sector in bill, bipartisan infrastructure law, and about $11 billion in IRA to do with, we've spoken about 45Q, etc. But let me just give you some examples of what's happening and where we're seeing a lot of development for CCS. So we've got, within the bipartisan infrastructure law, we've got about $8 billion for CCS demonstration and pilot projects, testing and validation. So about $2.5 billion for CCS demos, so high technological readiness levels, about $2.5 billion again for carbon storage, testing and validation, about $2.1 billion for transportation infrastructure, another $1 billion for the low TRL CUS, CCUS projects, etc. So that's bill, bipartisan infrastructure law. And then we've got the Inflation Reduction Act, which expands 45Q, which is the carbon tax. And then there are the peripheral sort of policies that are technology agnostic, but will help industry, meet some of those costs for CCUS. So we've got things like procurement policy. So we've got about $5.5 billion for green procurement, and about $6 billion for clean energy demonstration. So beyond CCS, yes, energy efficiency, etc., but also it includes utilization. So that's what's happening in the US. And of course, there's a bunch of things happening overseas as well. And I can get into that, but I'll hand it back to you for now.
Thanks. Thanks, Ankita. It was really informative. Thanks for sharing this. Let me now switch over to Mrs. Devika Vattal, GCCA. Hello, ma'am. So I guess you are on mute.
Sorry.
No worries there. Yes, ma'am. So GCCA is working on a decarbonization roadmap for cement sector in a global manner, as well as what we heard from you, you are also working on state-specific decarbonization target for cement sector as well. Ma'am, are you there?
Hello. Yeah, I think I just lost what you said. Would you please repeat?
Yeah, no problem. No, I was just mentioning the GCCA is working on a decarbonization roadmap for cement sector in a global sense, and as well as national level roadmap is also being planned for India. So, ma'am, could you quantify the role the CCUS could play in the cement sector, particularly from Indian standpoint, till 2030 and post 2030? Could you quantify it in terms of what is the mitigation potential you expect from CCUS for India in cement sector?
Sure. So I'm sure you have had a chance to go through GCCA, which is the Global Cement and Concrete Association. The headquarters are based out of UK, and GCCA 2 years back launched the global roadmap for how the cement industry can mitigate, the CO2 emissions, which, as I think some of the presentations that we saw, most of the experts have already covered that 60% of emissions in the cement come from they are related to the process. There's nothing you can do about those emissions. So when GCCA launched the roadmap, and in the roadmap, we had different options of mitigating CO2. And one of the options which came out to be the most promising, or something that maybe to 2050 or beyond, is CCUS, that has the most potential for having or doing CO2 mitigation in cement. Yes, there are other options as well. We have electrification. We have maybe there are different things that you can adopt in a cement industry. But just so that I understand, there might in the audience there might not be people from cement. A cement plant's life is 50 years. So it's not that a new technology comes in and we can just, quickly change part of it and it will work. It doesn't like that. The cement plant will run its life. So, and we cannot just change at, just because we think it is important, we cannot change it. So I think the potential that CCUS has, it is immense. But at the same time, when we look at India, it's a growing economy, and without emphasizing on the fact that India and China are the biggest manufacturers of cement. So I think we have reached a state when it comes to CCUS acceptance that yes, it is something which is a prime requisite. We cannot keep waiting for US or UK or any other nation to be, take the lead. And yes, they have policies in place. Whereas in India, it's not that we are working on different fronts, to be honest. And, like some of them already mentioned, the major aspects for CCUS is not only technical. Technical is a very small part of it. And technical implementations are already, they've already reached a level where we have bigger scale up, the bigger scale ups have already happened. Some of the technologies are well known for, as Gaurav clearly mentioned, they have been as old as 40 years. We have been used a basic amine process for as long as I remember. And, so the technology aspect is not the only thing that we have to look at. When it comes to policy, India is also working, some of the policies they already mentioned, that India recently launched the CCUS policy in last year, November last year. Then we had a climate policy initiative launching another CCUS initiative in May this year. And, and just to add to that, India is also closely working with SEM CCUS, SEM, which is Clean Energy Ministerial's CCS initiative. which also tells you that we are working at policy frameworks. We are working at a technology. We know what is working, and for technology, one of the biggest aspect which needs to be considered is one size will not fit all. So even though when it comes to technology, the most important factor is your site. Where is the site? What is the location of the site? So I think to be honest, I think these and these kind of things are happening. We are seeing a lot of feasibility or pre-feasibility studies being conducted, not only in cement or in steel. They are happening in every sector. And the third most important part is the economic part. Like they're asking questions: who's going to pay for all this? Interestingly, I've seen a lot of interest from the multilateral banks. They are providing, when we talk about, yes, everybody talks about climate finance, green finance, but I think what needs to be understood is for hard to abate sectors, transition finance is something that we should be looking at, because we are trying to transition a very hard to abate sector, moving them and incorporating CCUS, which itself, the return of investment is very high. So,
Understood.
so I think these three aspects are critical, and it's great to see that India is working on all fronts. We might not be there yet, but I think we are gearing up to be there. Yeah.
Thanks, ma'am, for the detailed explanation there. So let me move to Ramachandran Gopal. Hello, sir. Thanks for your time for joining this webinar session. So TAGFET has 60,000 tons of CO2 being mitigated for producing baking soda. So, and also when we spoke with the other panel members so far, one point is scalability is also a matter of concern. So TAGFET has an industry scale CCUS model, and what is your view on the scalability of CCUS projects, sir?
Yeah, thanks for the time and the invitation. So all the talks so far were policy related, whereas I'm going to speak from the point of view of practically what are all the problems that we faced and how we slowly came out of the problems. Okay. Number one, on the scalability, the plant that we have what we have installed is about 174 metric tons a day of CO2. Okay. But there are plants in the world operating, for example, in a refinery in Houston, 4,250 metric tons a day. Okay, so scalability is not at all an issue. It is a well-proven technology. See, and it is of the 2-3 options that are available, the more easy to operate and cost-effective is the one which is solvent-based. Okay, at the moment. And even though people said, this is the cost of CO2 production, etc., what we practically found after implementing the plant is that it is not less than $50 a metric ton. Okay. But fortunately for us, the product that we produce, because we are using this carbon dioxide as a raw material in production of not baking soda, but light soda ash, which is a raw material for making detergents and glass. Okay. So we could afford that cost. Okay, we could absorb that cost. Okay, but not many industries can do that. Okay, because the CO2 is considered available free in an equivalent soda ash plant called the Solvay project, where it comes out of the lime kiln. Whereas in our case, since we don't have source of carbon dioxide, earlier we were getting it from the adjacent fertilizer plant. But since they started using the carbon dioxide in full, we had no other alternative but to implement our own project. Okay, out of necessity, we started this project.
Understood.
Okay. But we found that it is possible to go to any scale. In fact, we have started building the second plant already because we have started expanding, because the carbon footprint of the soda ash that we produce is only 0.79 tons of CO2 per ton of light soda ash. Okay, whereas the equivalent product by the Solvay is the 2.12. So many multinational companies who are producing detergents are really interested, who are committed to the net zero, to use this soda ash because it is going to help them in reducing the footprint. Okay.
Understood.
And judicious use of green ammonia in place of the gray ammonia that we use in the ammonium chloride production, and also use of biomass in the boiler would make this product carbon negative. Okay, that's what we have found. We did an LCA and found that it will become a carbon negative. So we are into programs on this. So our biomass fired boiler will be commissioned probably in about a month's time, and this will bring down the carbon footprint to 0.4, and then we are negotiating for a green ammonia shipment from Egypt. Okay.
Okay.
In case we get it, probably, it will further, it will demonstrate to the world that yes, it is possible to produce green soda ash. Okay. But someone has to, because the price differential currently, because of the recession now, the ammonia prices have came down crashing. Okay. And it is, someone has to bear the cost of difference between the green ammonia and the green ammonia. Okay. Either in terms of a higher selling price of the product or product differential where the consumer pays or who pays. But in order to continue with these activities, there should be, I don't want to call it a subsidy, okay, but some methodology by which this cost is addressed, is passed on to the consumer, who finally is the main reason for all this carbon emission. Okay. So coming back to answer your question, scalability is not an issue. Operability is not an issue. It is a well-proven technology, but cost is not like what people are saying. Okay, it is not less than $50. Okay, currently, since we have a lot of advantages in our plant, what we have designed, we are approximately, it is around $52 now. Okay. Okay. But we have tied up with IOC, who have developed a technology to use immobilized enzyme structure. Okay, in the. Yeah. So, and as per their technology, we expect the cost of production will come down by at least $15 a ton. Okay. So we expect it somewhere around the vicinity of $35. Okay. So whether it will further go down, okay, because many industries cannot, there are many industries required like methanol, etc. Okay. You cannot produce methanol with this high cost of CO2 unless it comes down to $25 level. Okay. So we should work towards the technology to how to bring it down to $25. Okay, that's what as per our chairman, we are committed to this, and then we are working on that. So I hope we succeed and then demonstrate this IOC's technology that it is possible, and many CO2 plants which are already operating probably will retrofit their plant with this technology. Okay, that's what we hope.
Understood, sir. Okay. Thanks for a very detailed answer on how are you managing this current CCO plan, and also based on the positive news that there is opportunity for reduction in cost as well as scalability not being an issue is a very good thing to hear. So just we have five more minutes, so let me just quickly go to the policy aspect of thing. This session will be open to all the panel members who are interested to take the question, can answer the questions. So number one thing is, during the recent ministerial talk with Ministry of Steel in India, they mentioned that to aggregate the demand for green steel, government will be taking some orders as a way to create a demand for green products. So in any way, do you see there is a probability or chance for demand aggregation by setting up a mandate similar to the approach they took for green hydrogen as well, where they tried to have a mandate for fertilizers and refineries? Can it be one of the way to provide a demand for taking up CCUS related outputs?
I have a question on this.
Yeah.
See, for example, we have an ammonia plant where the capacity is 1,500 metric tons a day. Okay. But the reformer portion which we retrofitted can produce gas equivalent to only 1,350 metric tons a day. Okay. So that means in the synthesis section, I have 150 metric tons per day of spare capacity. So we have now worked out a scheme wherein, we will implement a green hydrogen electrolyzer, okay, next to our plant, and then route this hydrogen and produce green ammonia by sourcing renewable energy for the additional portion, proportionate portion from 350 to 1,500, okay. But the cost of production based on the electrolyzers that are available now, okay, choice of electrolyzers, etc. So it is really frightening. So someone has to build this. So is there any method by which, is there by means of deferment of taxes or something like that, is there anything being worked out in the policy framework? Because I heard that Niti Aayog is doing something. So are you privy to any of those such kind of information so that we can develop this project?
Only thing that I am aware of is for green hydrogen related projects, there is states are planning for a capital subsidy for the infrastructure, and all other aspects are a little bit muddy. So I cannot say for sure, but states, even the state that we are currently working on from our institute, the states are trying to have a capital subsidy to be offered for green hydrogen related infrastructures.
Yeah, for example, in a green hydrogen plant, as you know, the raw material is a renewable energy, and then the energy is not available at the current cost at less than 4 rupees 70 paise, okay, at your doorstep. So at this level, you can never produce the green hydrogen.
Yeah, yes. I also seen some. Yes, Ms. Devika.
Thank you. So quickly, when you spoke about the policies or, how they are doing, last year, India launched their CCUS policy, and I think it was mentioned in detail. We are obviously taking inspiration from what is happening in the US, what is happening in Europe. Our policy framework will definitely come from there. But what was discussed was, maybe the framework for, using the credits or carbon-based incentives, it would be in a phased manner. It would be done in a phased manner. So the first phase mostly talks about carbon credits or carbon incentives that will be provided on how you have lowered the footprint, and that is one phased approach that they had, and which will be followed secondly by the second phase, which will introduce carbon tax, but that will come at a later stage. So like Shripati already mentioned, some of the policies are not 100% there, but the introduction of these policies really helps in streamlining. And I would just like to add to what Shripati was asking a question. I think I'll make a very simple statement here. Technology can either make money or it can save money. Otherwise, the technology it will just be somewhere else. It is of no use to anyone. So so the question, Shripati, that you asked, I think this statement kind of answers it. If we do not have policy frameworks in place, if we do not have drive for industries to adopt CCUS, you definitely need, the country itself needs to, we have to think about plan B, plan C, plan D, whatever plans we need to incorporate and encourage industries to adopt CCUS. So, we have to take different kinds of mandates so that we can get there. That's all I wanted to add. Thank you.
Thanks, Devika. Ankita, I also see your hand.
Yeah, I just wanted to directly address the procurement question, and from a global perspective, we definitely see procurement as one of those really main policy drivers. And even though it's technology agnostic, it is the type of carrot-based policy that will propel CCUS forward, because if we look at within the US, we have the federal Buy Clean initiative, and we've got these Buy Clean initiatives across the different states. But if we look globally as well, we look at the industrial decarbonization initiative, and India is part of that. The US is also part of that, along with 7 other countries. And this is all for the government to procure green products for steel and cement. And they're setting standards, some very ambitious standards for what green means. And to meet those standards, then, even though you are technology agnostic, you're going to need CCUS as an imperative. And so so I really see these as market signals, and then there's talk of advanced market commitments, etc. So those signals are definitely going out to industry from within government and also from within the private sector. So we've got the First Movers Coalition, etc. And so these are definitely, procurement policies are definitely the type of policy that will propel this technology forward.
Thanks, Ankita. Thanks, Devika, for your responses. One thing about CCUS is I am trying to see the parallels, if there is any possibility with respect to National Hydrogen Mission. And this question is directed to Gaurav. Is there any problem relating to the value chain of CCUS in your perspective, Gaurav?
Hydrogen, yes, it has a hydrogen is a potential fuel for tomorrow. But at the end, as we already discussed during the panel discussion, the cost of hydrogen which is being produced will definitely play a big factor in how quickly it is adopted by different industries. So let's say for once, let's say we forget about green hydrogen, blue hydrogen, or whatever hydrogen. If the hydrogen is being produced by coal gasification, the price is very less. It comes down to $1.50 per kg. If I integrate that system with carbon capture, it is a clean system. So if we have to see in this perspective how we can reduce the emissions, and as well as we found economics with whatever we have. We have been blessed with coal. We don't have oil and anything.
Yes. So
Answer will be in this regard. So if we are making blue hydrogen, yes, carbon capture will be required, and then in turn blue hydrogen can be used in most of the sectors, because hydrogen has some inherent advantages as well.
Understood. But this complementary nature, will it feel complementary if one policy support for one technology comes before and it started getting some investments, and the subsequent complementary technology, it kind of takes a backseat, right?
Again, technology which is viable, feasible, which gives better cost economics will have the way.
Okay.
But even ministry, let's say, just coming to Ministry of Steel, they are actually proactively working on this, and they have also got some R&D fund, and they are trying to promote the usage of hydrogen-based DRI and modification the existing DRI systems for some amount of hydrogen. And also they have asked for proposals which for modification in the blast furnace system so that it can accommodate hydrogen to replace the coal.
Yes, understood. So one last question, again, it's an open question since we are way past the time of the webinar session. One prominent thing that came was who will bear the cost, some kind of green premium will be needed. And again, as one of the established policy in India, based on green hydrogen policy, the green premium needed won't be so far beyond the capital subsidy that can be offered to the infrastructure cost. So it may be dependent on the demand that is being there for green products. So that is what is needed. Any recommendations from any of the panel members?
Any technology at the initial stage, it's always expensive. Someone or someone else has to bear the initial delta cost. So whether government comes to the party and give the subsidy to take care of that delta part will be the most appropriate way, or else the best scheme is which does not require any support from the government. Likewise, which is being done at Tuticorin plant by Mr. Ram sir.
He had his advantages, but yeah, that makes sense. Ramachandran sir, any comments from your side?
Yeah, I agree, but I'm slightly, I would like to take you back by another 40 years when there were no effluent treatment plants in India. Okay, even in fertilizer plants, I have seen fertilizer plants. Okay, large fertilizer plants without effluent treatment. Okay, so people were forced, unless and until Pollution Control Board, you get a consent order or environmental clearance, etc. You don't implement pollution control measures. So like that, I don't think, you need any capital subsidy, in my opinion. Okay. In our case, we did it out of necessity. Okay. It may not be true, but going by the amount of money that we spent, I don't think it is a huge capital expenditure compared to the main plants, which it is going to support. Okay.
Understood.
Where you require support is only in the operational cost. Definitely the additional operational cost, it has to be passed on. Otherwise, it is going to eat into your current profitability. Okay.
Thanks. Thanks so much. Devika ma'am, I see your hands raised. Yeah.
Yeah. So, I would say that it's a very fresh and a good perspective that Mr. Ramachandran said, industry has to take an initiative and, we have to lead by example. I think Tuticorin this is exactly what Tuticorin has done. So I think it is quite commendable. It's India's first CCUS plant. So I think, you mentioned it in a very positive way. But to answer to your question, when it comes to, we talked about policies, we talked about technologies, but, the liability for who's going to pay for the CCUS, does it only belong to the industry? I would say that we still have mixed reviews, or I would say a mixed feelings for it. Even we have to understand hard to abate sectors. It's not a sector that we can decide, okay, we don't need it anymore, and then maybe we move on to a cleaner world which does not have such technologies. But we can't do that. These are there, if in your economic growth as a country. I think these are the major pillars for economy for a country like India. So when it comes to investment at such a high scale, yes, it is very expensive. And, lead by example, yes, some can do it, but others, it might not be easy. To adopt a generic guideline across the sector, I think everybody is nodding head. So, you can imagine it's very difficult as an industry coming together and deciding we will do this and this is how we will approach, the capital. So just to finish what I was saying is, a multilateral banks, like if you look at Asian Development Banks or World Banks, they have been working with different industries, like they're talking about clusters. So even the cement is like I work with, I work with GCCA, but prior to that, I was working as a carbon capture expert with Asian Development Bank. And we did a feasibility study for a cement company in India. And what we were trying to figure out, what will be the total cost of the plant? Just to give you an idea, like I think Ankita already mentioned, when we talk about a CCUS project, it is not a year-old project. It's a 2-year-old project. It goes from anything more than 5 years, because it's not only the technology you're evaluating. You're looking at what policies do we have? Does it fall in that category? What kind of economics is it talking about? And then it's a complete different ballgame when we talk about storage and utilization. If I start there, we might have to add more to this. But what I'm trying to say is, it is, in my experience, what I've seen is every industry is facing with this challenge for CCUS, implementing CCUS, finance, policy. But what I find interesting is the only answer to all these problems for solving this puzzle is working together. Collaboration is the only thing which will bring us much closer to what our targets are. Otherwise, if we all are working in our own kitchens thinking that we are going to do something great, I think it might not, that's not the answer. At least that's what I firmly believe in. Collaborating is the only way we will, reach there faster.
Understood. Thank you. And yeah, thanks for the panel members for your time. It's well past 4:30. So let me close the session here and hope the audience got some imagery on India's possible sectors that are scope for CCUS and how should the industries be prepared and what are the policy interventions needed forward. So I will just hand it over to Abhishek. Abhishek, over to you. And I will also request everyone to switch on their videos, switch on their camera so that we can take a screenshot of the session.
Thank you, Sripati, for that informative panel discussion. I think we all have takeaways from this panel discussion. We have a lot of elaboration on various aspects and technology consideration that we can look onto. I am really very thankful to all the panel members to devote us some of their valuable times and to be here with us and to elaborate on the CCUS technology and the points related to it. I think just to summarize, all the consideration that we have, we talked about the whole capturing, utilization, and storage model, the pre-combustion, post-combustion, and oxy-fuel combustions, the utilization part of it, the enhanced oil recovery, the chemicals and fuels, and finally on the storage part, where we talked about geological and ocean storage. Further moving ahead, we also talked about the potential that has been assessed in India at 600 gigaton for carbon storage, and the challenges in terms of the technology readiness, the cost and scale, and the infrastructural tech challenges, and the regulatory framework that would be associated with it. Further, we also learned about the profitability, particularly in the ethanol manufacturing, the natural gas processing, and hydrogen-based applications for the CCUS as of now. And we also learned about the hubs and cluster model, which can be used to scale up the CCUS adoption in countries, and how the shared infrastructure lowered will lead to a lower capital cost and will lead to a lower risks factors, and generally by the economics of scale will help help to further enhance the usage of it. Further, it was also elaborated, how the global partnerships is highly required, the technology transfer that should be, considered in this particular domain for maximum adoption. And, we talked about the global development, specifically in the countries of US, Canada, Denmark, and, European Union and the South Korea regarding this technology. Further, it was also elaborated how the steel industry can lead the CCUS deployment due to its push for expanding production capacities. And finally, lastly, on the policy aspects, we did elaborate on that. So I would like to thank you all, our designated panel members, and the and the people who joined us over this webinar. I think this was a very informative session, and we all had our takeaways from this. Ahona, are you there? I think we can have a group's photo session just before we conclude this webinar.
Sure, absolutely. I think I'm ready, and I'll just take the screenshot. Done. Thank you so much.
Thank you once again to everyone. The third part of the industrial decarbonization series, we would be informing on our WRI Twitter handle as well as on the WRI LinkedIn page. So do follow us for all the updates. Thank you.
Thanks.
Thank you.
Thank you so much.
Thank you.
Thank you, everyone. Bye. Thanks.